Okay, well here, we can use this simple model that we just created for a depletion mode field effect transistor to estimate a switching voltage, the voltage that we need to apply to the gate to get this transistor to switch from on to off. And even though this model is very simplified, it'll still be interesting to see how this works, okay? So here, let's go ahead. We're going to turn to the notebook. So here's the idea. We're going to try to estimate the switching voltage for an FET. And remember, we switch the FET by applying a negative voltage to the gate relative to the source and drain. In my drawing here, I've just drawn the channel and the gate and the source connector, but I haven't drawn the drain because I don't need it for this problem, okay? Very good. So the thing to realize first is that the gate and the channel are like a capacitor because they consist of two conducting plates that are separated by a gap, insulating gap. And the capacitance of the gate channel capacitor is approximately equal to the area of the gate times the dielectric constant of the insulator, which I'll write as the E sub R times E0. E0 is permittivity of the vacuum, divided by the distance between them, which I'll call D, okay? Okay, moreover, if I apply a voltage between the gate and the source, or the gate and the channel rather, I can accumulate charge, okay? And the charge that I would accumulate would just be equal to the voltage times the capacitance, okay? Now, the reason this works is that because the channel is a doped semiconductor and doesn't really contain a very high density of free charge, we can easily apply a voltage to the gate large enough to push all of the free charge out of the channel. So if we induce a positive voltage on the channel, such that the induced voltage is equal to the total amount of charge in the channel, then the device will switch. That means the channel will become insulating and it will be no longer possible to pass current from a source to a drain. Okay? Now here, of course, the total amount of free charge in the channel is just given by the density of electrons in the channel times the charge per electron times the volume of the channel, which is equal to NdE times the area, okay, times the thickness of the channel, which I'll call T. All right, well now we're ready to get an expression for the switching voltage, okay? And it couldn't be easier. The switching voltage, that will be equal to the voltage where the induced charge is equal to the total charge in the channel. Okay? And so this will be N sub D times E times the area times the thickness. That's the induced charge. And then we have to divide by the capacitance. Area, dielectric constant, vacuum permittivity, divided by D. So the D goes in the numerator. Notice in this expression that area cancels out. And so we're left with N sub D E times T times D divided by epsilon R epsilon naught. All right? Now, here, let's put in some reasonable parameters. So these are reasonable numbers, but I will admit, I'm choosing them to get a reasonable voltage in the end. So let's suppose that, excuse me. Let's suppose that ND is equal to, say, 2 times 10 to the 23rd electrons per meter cubed. So that would be a heavily doped channel, but not that heavily doped. Let's suppose that the distance between the gate and the channel was 0.1 microns, or 100 nanometers, or 10 to the minus 7 meters. And let's suppose the channel thickness is likewise 100 nanometers. And finally, let's suppose that the dielectric ratio for the insulator is 11, which is what it is for silicon, okay? And let's suppose, of course, epsilon naught is a constant, 8.85 times 10 to the minus 12, okay? Then we can put in numbers to figure out what the voltage is. The switching voltage then should be, well, we'll just put in the numbers, 2 times 10 to the 23rd. I'm going to leave out the units, otherwise I'll completely cover this page, times 1.6 times 10 to the minus 19, times 10 to the minus 7, times 10 to the minus 7 again. I'll just combine those here, 10 to the minus 14. Divided by 11 times 8.85 times 10 to the minus 12. Okay? Great. Well, now go ahead and figure this out. It'll just take you a moment. Okay, did you get it? So what you should find is that the voltage in this case is about 3.3 volts. So by using a transistor with perfectly reasonable parameters, we can get a perfectly reasonable switching voltage of a couple of volts, okay? Of course, we shouldn't take this problem too seriously. It's a very simplified model, but still, it gives you an idea of how this works. All right, let's stop here.